Engineering from IIT Bombay, Mumbai. After completion of PhD, she has done her postdoctoral research in the School of Electrical and Electronics Engineering, University of Manchester at Manchester, UK, and in the Department of Electronics Engineering, Mid Sweden University, Sweden. Currently, she is an associate professor in Indian Institute of Technology, Mandi. Her research interests include converter topologies, modeling, design, and control, which focuses on electric vehicle, storage technology, wide bandgap device like GaN and silicon based applications, reliability analysis, and high frequency magnetics. She has also conducted a 12-week NPTEL course and on NPTEL under the wide bandgap devices. Now, I request our chief guest, Dr. Moumita Das, to handle the session. Ma'am, please.
Okay, thank you. Thank you for a nice introduction. So I'll start my presentation now. So today I am going to talk about this wide bandgap devices, as you mentioned, GaN, silicon carbide, and their application in traction. Just a minute, it's not working. I'm unable to move to the next slide. Oh, just a minute.
Okay, ma'am.
So when I'm sharing, I'm not able to move to the next slide. So you can share my, you can see my screen, right?
Yes, ma'am. We are able to see, ma'am. We go ahead this mode, ma'am. No problem. Please go ahead.
Let me try. Now it is working.
Yeah, now it's working. Okay.
Okay. So the main motivation behind looking for this traction or the EV application. So as you know that overall energy consumption, so like it is mostly the biggest part is like biggest share is from the transportation sector, one of the major portion. So that is why it is expected to have like around 44% share by 2035. So this will increase use of fuel usage, and then again like greenhouse gas emission and all the problems related to this will increase. So then what we need to do? We need to look for alternate kind of solution. Again, it is not moving. I think I'll just uh, make it in this PPT mode and then I'll present. So there is some problem with the sharing, because when I'm sharing,
sure. It's not a problem.
so it is like it is not allowing me to go to the next slide. So okay. Okay. So this is going to increase, so that obviously it is going to cause many problem. So these problems, one of them, you know, as that global warming or climate change, that air quality issues, all these problems will increase eventually. So then what we need to do? So like I'm starting from this like introduction of this like traction or how we are going for this. So then what we need to do? We, in order to address this problem, so what we can actually look for like alternate kind of fuel. So as you know, like there are like renewable energy related research, many things is going on, and so then that probably will help us to reduce dependency on the fuel, and then we can also develop energy efficient vehicles, and we can go for different kind of like sources, like which probably vehicle will depend upon based on lithium and batteries. So they can actually reduce the use of fuel and then fossil fuels, all these things. So then in order to use that, what we need to do? So we need to look for the solution which will enable us to go for this kind of solution. That is one of the major component is power electronics converters. So this lithium ion batteries, as you know, so like they have like high power energy density, long cycle life, low self discharge rate as compared to other batteries, and this is the main component which currently used for many applications along with renewable energy, traction vehicles, and many places there people are using this kind of batteries. So now in order to use these batteries we need to have like efficient kind of power electronics converters. So in order to go from complete dependency from these fossil fuels, we have to look for either renewable energy based solutions or maybe some alternate solutions. Again, like in order to use that we need to have like conversion medium, and then again like how we can convert this, we need to have power electronic system. So in order to have power electronic system, the main component of the power electronic system, what it is, so this already you know, so this is like very basic thing. The main component of the power electronic system is the semiconductor device. So semiconductor device generally what we use in the power electronic system, mostly silicon based semiconductor devices. Now people are going for this different wide band gap kind of devices. Now what is this wide band gap? So as you can see, this different types of material, like you can see here in this particular slide, so it is like metal, semiconductor, then insulator, how their band gap are different. So metal means it is having overlap, semiconductor the slight difference is there, and insulator the difference will be much higher. So then this is the band gap, so basically difference between the energy gap which is actually represented here. So this band gap for silicon, so the band gap whatever it is there, whenever we go for wide band gap kind of devices, it is much higher in wide band gap devices. So you can say see here, so if we consider semiconductor, the band gap whatever we are having, it is much higher in case of insulator also, right? So then can we use it as wide band gap devices? No, obviously not. It depends upon the material property. So what is the difference between different silicon, silicon carbide, gallium nitride, or the wide band gap devices? So when we see material property, so the main thing which we are looking for, you know, like solution which will be suitable for modern application. Modern application means like there can be different application. One of them is traction. So now modern application where what we want high power and energy density, as you have seen for lithium and batteries. So now in order to use that, so for that we need to have material which will be lower in size, which will have high power density, and then which can also be used for very efficient or high frequency, high temperature kind of application. So you can see here the silicon, so this band gap is 1.12 ev. So you can see here, hopefully you can see the my cursor. And when we go for wide band gap devices, why we say this wide band gap, so for silicon carbide or gallium nitride, you can see this band gap is much higher than that of the silicon. So it is like 3.26 ev for silicon carbide, 3.5 ev for gallium nitride. Now why we need to go for this kind of devices? So what it helps us? So when we consider these devices, so basically what we will have, so you can see here the differences of silicon, silicon carbide and GaN in terms of electric breakdown field, thermal conductivity, electron mobility, saturated electron velocity, and energy gap. See, on with respect to all the properties, you can see silicon. So, like silicon is the like smallest portion which is shown in this particular diagram. So this is here it is the silicon device property. So now if you see silicon carbide or GaN, it is having much better property than that of the silicon, but it is not insulator. So you have seen in the previous slide, insulator is also having much higher in band gap energy than that of the silicon device. So basically band gap is much more in case of insulator, but silicon carbide and GaN, they have wider band gap, but they are not insulator. They have better properties in terms of breakdown voltage, thermal conductivity, or probably the frequency part. So that is why these devices are like kind of solution for this modern power electronics application. So you can see here, so one of the like device is shown, so silicon MOSFET, which is having like same rating that of the silicon carbide. So silicon carbide size is much lower than that of the silicon. it is 110 times thinner and then 100 times of higher doping concentration. So these properties are much better in silicon carbide for same kind of rating. So that is why people are moving towards wide bandgap semiconductor applications. So what are these applications? So if you see here in this particular graph, so this is the silicon, you can see. So like now majorly the application whatever you see around yourself, so it is silicon based applications. Till now industry is like kind of it is using silicon because you know it is easily available, it is much cheaper, and also the manpower which we need in order to develop any system, so they are trained in silicon based system. So that is why silicon based applications are all around you. Slowly we are moving towards silicon carbide or GaN based application. It is still I mean we are there, like we have research level application in GaN or silicon carbide. Some of the industries they are now working towards like kind of transition of from silicon to silicon carbide. So those applications are, you can see here. So GaN, so these are the applications of GaN. So GaN is one device which is suitable for a low to medium power kind of application, but it can go to very high frequency. In fact, radio frequency applications are kind of one of the applications where GaN is suitable. So here you can see here different type of like low to medium power whatever application you can see around yourself, either consumable electronics or like high power applications. So they are GaN as shown. So you can see here this blue and then dark blue and the light blue shaded portion, it is shown for this GaN application. Now the green one, it is shown for silicon carbide. So silicon carbide is the device which is suitable for very high power, high voltage application. So here it is shown for like 6.5 kilovolt kind of device. It is like the silicon carbide device is available, and also like it can suitable. It can be used for like megawatt level, 10 megawatt plus applications. So the mostly the commercial kind of applications, industrial drives or like railway applications or powertrain or so basically commercial EV charging, and then renewable energy integration with the grid and industrial UPS, all very high power applications, so where silicon carbide is mostly suitable. And for low power, low to medium power and high frequency, GaN is suitable. Silicon carbide can operate at higher frequency than that of the silicon device, but there is a limitation of the power. So if we want to go for like 10 megawatt plus applications, so there the frequency level is limited. So if we have like lower power, then it can go for slightly higher frequency than that of the silicon devices. Okay, so now so this you can see here. So like power versus switching frequency, where this like what kind of devices are suitable. So as you can see, silicon device, it is shown here in this gray portion, and silicon carbide and GaN. So silicon carbide is the orange one and GaN is the purple one. So GaN, to like as we are going for higher frequency, you can see here application of GaN is more, and as we are going for high power, so their application of silicon carbide is more. Silicon currently is in use for all kind of applications. Again, like there is some limitation of switching frequency, temperature, and efficiency. All these limitations are there. So that is why we cannot improve the system efficiency or system reliability beyond a certain limit. Okay, now you can see here this market potential for this wide bandgap semiconductor device. So you can see as per the like expectation. So the GaN potential you can see here. So like it is like in 2022 it is 1% market penetration, and then 2026 it is expected to be 16%. And this is how it is going to be. And similarly for silicon carbide in 2020, so it is like 14%, and 2026 it is expected to be 46%. So it is going to like it is expected to replace like major like application like in industry applications in of silicon. And this harnessing of new power, so gallium nitride and silicon carbide, it is actually considered to be like new and emerging design where silicon cannot be useful. So like silicon having some property limitations, so there these devices can play important role. And the current trend is one of the important trend is the automotive applications, obviously, and the consumable electronics. So there these devices fits very well. And then future projection is that both GaN and silicon carbide technologies exceed $20 billion annually by 2026. Now, what are the differences? So you can see the property of the silicon carbide and GaN semiconductor structure. So you can see here. So silicon carbide structure, if you see, so it is like quite similar to that of the silicon device. If you see, if you remember the silicon structure here, I don't have the silicon structure. It is quite similar to that of the silicon. Only difference is that you can see here instead of silicon material, we have the silicon carbide. So this is the difference. But structurally, it is same. Again, like it is having obviously this planar gate depletion MOSFET, vertical double trench MOSFET, or vertical cascode JFET. So all this kind of structure is also available for silicon device, but property wise this material is better. But in case of GaN, it is actually structurally also different. GaN material is different, but structure wise also it is different. So it is actually, if you see the current flow, so basically one two-dimensional layer is formed between GaN and AlGaN layer. So there is not actual layer. So if you see the GaN structure, so basically if you see any device, silicon structure or the GaN structure, GaN is basically, it doesn't have any, like if you see structure wise also, so it doesn't have any inherent diode. And the voltage level of this gate in case of GaN, it is very low. It is around 6 volt maximum, and minimum it is minus 4 volts. But in case of silicon carbide, maximum volts is similar to that of the silicon. So same kind of driver can be used for silicon carbide device as compared to silicon. So that is why transition from silicon to silicon carbide is much easier, because you know the one of the main limitation is that supplying the gate voltage. So that is already available for silicon device. So we don't have to do much for silicon carbide device. So it can be easily used for any kind of application where silicon is currently in use. But in order to use GaN, again, like we have to consider all the like system structure based on the GaN requirement. As I'm saying you, the driver voltage and all these things, it will be much much different than that of the silicon carbide device. So that is why in order to use this GaN for industry or any consumable applications, so again, like proper system development is required. Not only system development, again, like we have to see the reliability and different aspect of this GaN based system. So for that, the transition will take much more time that of the silicon carbide device. Okay. So you can see here, so as I was telling you, so whenever like there is a drain to source current flow, so current flow, what happens, you know, like when the voltage is applied, so you can see here, this is two-dimensional electron gas channel. So this pink line, so like whenever this current is flowing, so you can see here through this channel, so it is not actual physical layer. So this channel is formed between drain and source. So this channel will allow the current to flow. Okay, a lateral two-dimensional electron gas channel formed on AlGaN or GaN heteroepitaxy structure provides very high charge density and mobility. For enhancement mode operation, a gate is implemented on to deplete the 2 DAG at 0 volt or negative bias. A positive gate bias turns on the 2 DAG channel. Okay, so like 0 volts can turn off the device, but generally what happens, you know, like for GaN, it is advisable to provide like plus minus voltage, means like maximum voltage if it is plus 6 volts, then minimum voltage instead of 0, some negative voltage is provided, because you know, like the like turn on voltage, so basically the voltage which can turn on the gate, the minimum voltage is very close to 0 volt. So then what will happen if we have 0 volt, some small noise or anything can false turn on the device. So that is why it is always advisable to provide the negative voltage, and it works like a MOSFET except with better switching performance. It can like go for much higher frequency than that of the MOSFET. As I was telling you, for radio frequency application, it is used in megahertz, few tens of megahertz kind of system. So where these devices are used for megahertz frequency. Okay, so you can see here, so this is actually one of the GaN devices. So here you can see different layers are formed, and this is as thin as paper, like slightly thicker than the paper. So, and then this is SMD kind of device, and mostly the component connections are at the bottom part of the device. So what happens, the PCB designing is also very difficult, and it requires special type of skill in order to use these devices for particular application. So that is why the requirement of manpower is also there in order to use this device for industry application. But if you see silicon device, silicon carbide device, so it is having same structure as that of the silicon. So use of this particular device or handling this device is much easier than that of the GaN device. And in case of reverse conduction, you can see here, so for silicon carbide, so it is having like this reverse diode, that generally what you see for silicon devices for MOSFET or IGBT. It uses this inherent or the body diode, so in order to provide current path in the reverse direction. But in case of GaN, there is like absent of this particular diode. So there is no diode in the GaN. So the reverse recovery loss is zero, because you know this is having parasitic body diode. So for any device, say silicon carbide or silicon, so obviously it is having some like kind of reverse recovery charge, although like nowadays it is expected this reverse recovery charge will be close to zero, but some charges will be there. So like but in case of GaN, what happens, you know, no parasitic body diode is there, so high dvdt darkness, so and zero reverse recovery loss. And this two-dimensional electron gas layer, what you have seen, this can allow the current to flow in reverse direction. So this is not having antiparallel diode, but still current can flow in the reverse direction in GaN. As you can see here in this particular slide, so reverse current path in case of silicon and silicon carbide MOSFET is through body diode. You can see here my cursor is not working, so you can see the first one. So where the current path is through the diode, and another one in case of GaN, it is not through the body diode or the parasitic capacitor, it is through the device itself in the same. So in case when the current is flowing in the forward direction, it will have exactly opposite arrow from drain to source. Basically same layer it is using for forward as well as reverse current path. So that is why even if the body diode is missing in case of GaN, still the current can flow in the reverse direction for GaN device with zero reverse recovery loss. This is actually big advantage in GaN device. Okay. So now if you see this type of GaN devices, so there are actually two different type of GaN devices. E-GaN configuration you can see here. The left one is the E-GaN configuration and the right one is the D-GaN configuration. So it is actually normally off, turn on with a positive gate voltage, it will turn on, and then normally it is off device. And cascade depletion mode device, it is actually normally on, requires negative voltage to turn this device off. Okay, so there are so like you have to see like what kind of GaN device you are using. Based on that, you need to provide gate voltage. So now advantages of this like wide bandgap devices. So I'm talking about only silicon carbide and GaN devices at this moment, because you know these are the devices which currently use currently available commercially for you can use it for any application. But other wide bandgap devices, they are still in research level, like gallium oxide or the diamond devices. They are the upcoming wide bandgap devices. Obviously they are having much more advantages than that of the silicon carbide and gallium nitride, but I'm not going to talk about those devices because they are still in research level. It is not available commercially. It is expected that they will have much better property than that of the silicon carbide or GaN. So like we can see their advantages whenever it will be available commercially. Okay, so now the advantages, as you all know, so loss reduction, obviously it will have much higher efficiency, it will have switching losses less, conduction loss is less, so then it is like it can improve the system efficiency. And second advantage is that it is having high power density. High power density means the size will be much smaller and better thermal characteristic, for any system. So as you can see now, people are going towards much more like lighter compact kind of system as compared to previous generation, right? So that is why these devices can be like very useful to further reduce the system size, where we will not like kind of have lower efficiency, we will have much higher efficiency, also system size will be much lower, right? Compact and efficient kind of system we will have. And obviously these devices are suitable to operate much higher temperature, so operation range can be also extended. And then obviously this like as you know, this like compact size and all, again like another advantage is that high switching frequency, what it will do, it will reduce the passive component size. So overall advantages of this silicon carbide and GaN are, they are like much more as compared to existing silicon device. So what are the challenges for future development of silicon carbide or GaN? So why can't we just use it? So one of the main challenges is that so this cost and availability. Since these are new device, currently the industry is using silicon. So that is why, you know, like since it is like bulkly produced and also like this is easily available, cost is much lower than that of the silicon carbide or GaN. Silicon carbide and GaN, they are new device, still very new. It is very much more expensive. It is like very like if the cost is much higher to produce these devices, since it is not that much in use for current application. So that is like very costly and not that available. Is not easily available basically. So, and also, like if we have to replace the existing system, we cannot directly go for that, right? So, integration of these devices need to be done like partly, right? Slowly. So this like integration, how it can be done, like new design, if they are like as per silicon carbide, so then it will be easier. As I told you, like gate driver voltage level for silicon carbide is similar to that of the silicon, then integration of silicon carbide will be much easier than that of the GaN device. So that is why there is a big challenge for like use of this device, like or replace this device to the existing system. So that this needs new technologies again, like new technologies in terms of driver or anything else which is required in order to replace the existing system with the system which is having these devices. That is why continuous research and development effort is required. And environment and social impact, so basically the focus is that you improve the efficiency, reduce the energy consumption for a positive environmental impact. But still, like until and unless we use these devices in actual systems, so that part cannot be confirmed. So that part also need to explore in order to find out advantages of these devices. Okay. So, like one of the applications where which I'm going to discuss is that, like different kind of charging, like on board, off board, or like how we can use it for the actual applications. So now you can see like in order to use the actual system, so basically different charging methods are available in literature. So if we consider the EV charging first, let's say like if we are going for like EVs, so then what will happen, the constant voltage type of charging, or maybe pulse and bark kind of charging, MSCC charging, CPCP charging, pulse current charging. So different charging modes are there, right? So different charging modes we can actually look for. So like how, what will be these different charging modes, and then how this is going to affect battery and the system. So ultimately we need to find out whether we are going to improve the system, or we are going to have like the system which is having like much less impact in order to improve efficiency. Okay, so one of the thing is that by using this thing we need to find out what will be the source. So source, if it is battery, we need to see what will be the battery aging, so which method will be suitable. So then this again like can be used for like different methods and to find out how this battery life can be predicted. Similar way, this battery life, the way it can be predicted, similarly we can also predict the device life. So how this device life is going to be in actual system. So for that, different algorithm we can use, actual system we can use along with battery to find out in EV how this system life is going to be, right? So now, so one of the application what I am going to use discuss in details is that onboard charger. So onboard charger for EVs I am going to discuss mainly. So basically, as you can see here, so like one of the important thing is that this onboard charger, if we are considering, so it is having the converter and then battery pack. So basically, like out from outside, using by using converter we can actually charge the battery, right? So whenever we are considering battery, again, like as I told you, so like two different aspect I am going to consider here. So one is the converter aspect and the battery aspect. As I told you in the previous slide, so like not in detail, so I just showed you like different graph. So basically battery life can also be affected depending upon the converter performance. And again, this converter performance depending upon like which kind of method we are going to use. So it is all interrelated. So the converter not only itself is going to give you like the better system, but also the peripheral devices. If it is connected to battery, then the renewable energy. So everything, the life of the whole system depends upon the converter performance in some way. So how it is depending upon, so one of the thing I am going to show you here, so is that, so battery, as you have seen, so like for EVs, so basically it is again like having different aspects. So generally what happens for a battery, if you consider any battery, so generally due to the temperature the battery performance changes, means the capacity, like if the temperature increases beyond certain limit, the capacity decreases. Again, like if like temperature goes below certain limit, again the battery capacity decreases. So you can see here the battery, this particular green and blue curve, so it actually shows with respect to temperature how the battery capacity changes. Now if the battery capacity is changing, so probably at only at one point, like one temperature, we are having maximum battery capacity, but we cannot ensure that battery will always operate in this particular temperature, right? So now here comes the converter part. Now converter, can it actually help to operate the battery in particular temperature where the capacity will be maximum, and that will help the battery to like optimize the efficiency, as well as we can use the converter device so that it can optimize the device converter efficiency also. So the problem what we are looking forward in this particular work is that like we are going to look for a solution. So like the voltage gain will be wide, bidirectional power flow, then like it is having the property of like loss reduction, and then it will reduce the design and complex control complexity. Just a minute. I'm actually not very comfortable with this because I'm not able to move properly. So like whenever I'm trying to move forward, it is not allowing me even in this condition. Okay, just okay. So you can see here. So this is the system. So where actually it is, we have considered the like different converters.
Request
So,
you can go for the presentation view.
uh,
And
then again, like it will go to the first slide, and somewhere I don't know, I'm stuck, or if I stop for some time, then it will be stuck there. Now it is working, but after some time it may stop. That is the problem.
okay, ma'am. Okay.
Okay, so like here I'm going to talk about this DC to DC converter, which is used for this system. So like there are actually many places it is in use. So like one of the thing is that a onboard charger, and then again like the inside vehicle. So basically to for propulsion and the charging discharging. Also it can be used. So it can have multiple kind of uses. The same converter can be also used configured for onboard charger as well. Okay, but like the main property, again, like I'm going to like go for like this wide bandgap device part. So here whenever we are considering these devices, so you can see here this is simple like resonant converter. Probably you all know about this particular converter. And we can obviously, as you can see, there are like different switches in this shaded portion. It is for reconfigurable purpose, means reconfigurable for like normal onboard charger, or just for the converter to transfer the battery energy to the motor, or from the motor there can be regeneration braking, so that can also be done. So the main thing here is that whenever this battery is connected to this particular converter, there is a resonant network. This resonant network is having, so you can see here this green shaded portion. So this green part is basically having like two different switches, inductor, capacitor. So these two capacitors, one inductor, and two different switches are there. Again, these two different switches are basically back-to-back switches, so that it can operate in unidirectional manner. So that is why this kind of configurations is done. Now, again, like it is actually shown for two different modes. So one is the power transfer, and another is for heating mode. And now these devices, all the devices are used silicon carbide device. The reason why this is silicon carbide device is because, you know, like the requirement of power is such that, so basically silicon carbide will be more suitable. Again, for onboard charger, obviously we can use GaN device, but the commercially available GaN device currently, it will not be suitable for very high power. Again, like as you know, the onboard charger, it is suitable for 3.3 kilowatt kind of power application. But like now this onboard charger again is, it is going for like higher power, means 22 kilowatt. And also battery for nowadays, like for EVs also, so they are going for like high voltage batteries, means like instead of like 48, they are going for 400 or 800 volts batteries. Again, it is having many advantages of going for this high voltage batteries rather than low voltage batteries. So that I am not going at this moment. So like if we have this kind of system, then like silicon carbide obviously will be more suitable considering the presently available GaN devices. Now, if we have silicon carbide device, what it can do? Again, it can have like higher frequency, and obviously it is suitable for this power, kind of power level applications. Now, the interesting part here is that this resonance circuit you can see here, so it is actually, you can see this is configured in power transfer and heating. In heating mode, it is having this one capacitor CR, LR and SH, this combination. And power transfer mode, it is having this CR, CP, LR, SA. So this combination, right? So these are the, and SH, obviously SH part, it is open. So that is why this part is not present in this particular power transfer mode. Now, here in this case, what is happening, the power transfer, as you know, like depending upon like which mode of resonant circuit we are working, whether we are going for ZVS or ZCS, whether the resonant network is working as inductive or capacitive, based on that we can actually go for ZVS or ZCS. So that can be done, and it will obviously have like the soft switching property, and this can give us like low switching losses, and all these benefits will be there, right? So silicon carbide anyway, like it is having much lower switching losses, so that is why this is not like major concern in this case. So the major thing is that if we go for higher frequency, so like the frequency which we have considered here, so this was around 200 kilohertz. So then obviously overall size of the system will reduce down. Again, this power converter size will reduce down. And obviously, if the losses are less, then the heat sink requirement will be much less. So it will be it will be actually suitable for like this, like anywhere, like you can fit it anywhere. So the major problem here will be the battery size. Other than that, the converter will not have any problem. Battery and the motor size will be the major concern. From the converter point of view, it will be like kind of like a much more compact kind of system. Now, heating mode, whenever we are considering, so like one part we have addressed considering the battery life. So battery life, again, like it can be affected for many reasons. One of the important reasons is the temperature. So can we like maintain the temperature? Yes, it is possible to maintain from the like converter side. So if you see here this resonance circuit, so by using the converter property, so like frequency if we can set, again like this will not be possible that much by using silicon devices because of the frequency limitation. So these devices can help to increase the temperature, so by using internal AC heating of the battery. Again, like internal AC heating can be also done by using silicon carbide. So this is the property of the converter, but again, like frequency limitation will be there. Again, the losses of the switches will come into picture. Here, the losses of the switches will be minimum. So that is why even if we use this internal AC heating, the efficiency of the overall system will not reduce down, but the temperature of the battery will increase. Again, the rate of temperature of the battery, how fast it can increase, again it will depend upon the frequency of the overall system. So if we go for higher frequency, then that it will help you to increase the temperature at higher rate. So that is why the wide bandgap devices will be like will have a major role for this kind of application. There are many other applications also. Again, like if we need to use this converter like in integration with the like if we can actually integrate it with the motor, so then again space can be reduced down. So you can see here this motor, if it is generally motor is having some heat loss, right? So these devices are suitable for that kind of like temperature operation, because temperature, wide range of temperature operation is possible using these devices. So again, like then there will be advantages to reduce the size further. So there are like many advantages. So this can be implemented by using these devices. So you can see here, so like in this particular converter, so this for onboard charger, so you can actually see here, so this is like bidirectional DC to DC converter. So in the power transfer mode, it can operate in both sides, like forward or the reverse mode. In the forward or the reverse mode, both sides, so like obviously it is not only having advantages here for propulsion or the regenerative operation, but also for onboard charger also. Vehicle can be charged battery, so like again like battery to like vehicle to grid operation will be possible. So this is again like both side the efficiency will be higher by using this wide bandgap devices. Okay. So again, it is actually shown here, this different gain ranges and the frequency. Different frequencies are shown, different actually configuration. So actually there are two different resonant network is playing a here role. So one is the CLLC and CLLCC. So these two different resonant converter you can see from here. One is like CLLC. So in this case CLLCC in this particular case, and in this case CLLC. So obviously this like this is there is also reconfiguration in the resonant network. Like some cases, like when the gain is particular level, so the efficiency will be higher for one particular resonant network, and for other cases the efficiency will be higher for another resonant network. Again, this is done by using the simple silicon carbide switches. Nothing else we have done here. So this is having like wide gain range, and obviously this gain range will help us to operate at different point depending upon the different time, because whenever the power is changing or the battery voltage is changing, depending upon the situation, gain range will vary. Again, the gain range, if it is varying, so depending upon that we want to operate at higher efficiency. So that is why the converter is always selecting different modes so that efficiency will be optimized. So this is one of the like lab prototype which we have used in the lab. So you can see this, I have just kept it to show you. So this is like probably you are not able to understand the size. It is very small type of converter, and it is like suitable for like for laboratory purpose. We have used 5 kilowatt kind of system. So it is having like very compact and compact size. So it once you place it inside the car, so like it will serve the purpose of like three different converter. So this simple converter can do that, and the heatsink and all requirement is very less because we have the silicon carbide switches. The switches are at the bottom, so that is why it is not visible. So the pins are you can visible here, you can see here. And also we have used this to see whether it can actually increase the temperature of the battery. So we have seen this, like we have tested it at -7 degrees Celsius, and it is able to increase the temperature to 19.1 degrees Celsius at 20 minutes. So this kind of system is very much efficient for this wide bandgap kind of applications. So as you can see here in conclusions, so these wide bandgap devices will allow the system to operate in wide frequency for in a wide applications. And then so this particular application where we have optimized the resonant parameter also, and heating can be done, frequency control. So again, like we can use that wide range of frequency control. Frequency can be adjusted because it is suitable for high frequency, so that is why frequency control is also possible. Again, soft switching is achieved throughout, so this is by using the resonant property. It doesn't have anything to do with the switch. And this proposed converter integrates power converter with internal heating. The converter has heating feature, uses common resonant network for heating as well as power transfer. So it reduces the converter stages by using deconfigurable structure. This proposed integration design is suitable for both battery heating at sub-zero temperature and power transfer in EVs. So meeting modern EV requirement. So this kind of system are also used for like very high power. So we are also like using for railway application. So we are using a different type of MMC converter, which is having some module which is based on this kind of resonant principle. So you can see here, this kind of resonant principle we are actually trying to use for this MMC kind of application. So where it will be suitable for railway application, the where it is actually used for like megawatt power level. So this kind of application we are exploring. So, and another thing is that we have also considered this EV charging station. So this charging station is having this integration of this, like I'll just tell you briefly about this. So this is the whole system. So like it is having like output kind of charger in it. So basically it is having wind solar PV integrated in it. It is having swappable station, so which can actually charge the swappable batteries. It is having 12 slot because we have lab facility for 12 slot. It can go for more than 12 or less than 12 depending upon the facility which they are actually installing. And then this is the NFC converter, which is suitable to like connect it to the grid. So it is having grid, different renewable energy sources connected, and this charging station can allow to charge the EV battery, which is considered here as the fixed slot, or swappable batteries can be charged at the same time. Again, the charging algorithm initially, which I have shown you, depending upon that this CCCB or the pulse and bulb, different method can be used to charge the EV batteries. All the devices you can see here, it is all based on this wide bandgap devices. So that is why I mean like overall charging station can be like it will not be huge. So one of the main concern of this high power charging station is the thermal part. So how this heat sink is going to be, if the devices are suitable for like wide temperature operation, then again this this problem can be reduced down further. Still there is some problem like how to connect heat sink and all these things. That part can be explored further like once it is in actual use, in actual application. So this is the entire system what we have for EV charger. So like it is having like different type of charging level. So like it is having like level 1, level 2 charging points, level 3 charging points. It can have like offboard charger, onboard charger, and then wireless charging kind of facility. So this integration of this renewable energy sources again will reduce down this dependency on the grid. So yeah, this is it for today. So like if you have any questions, you can ask me on this.
Ma'am, thank you for the presentation, ma'am. There are a few questions in the chat
Yeah,
box.
sure.
Just read
Okay,
out now,
can you?
ma'am.
Okay, so please, because if I close it, then again it will be difficult.
Sure, ma'am.
Okay, ma'am.
How does the converter manage power distribution between charging the battery and heating it simultaneously?
No, it is not happening simultaneously. Thank you for your question. So it is really a good question. So it's relevant very much. But like, yes, it is not doing both the things together. So like whenever it is operating in heating mode, the charging power transfer mode is not there. So whenever we are shorting this particular switch, thus we are considering this secondary part, this is obsolete. So that is why heating mode will take the battery to the level of full capacity. Then only it will operate in power transfer mode. Till that time, if only battery is there, so obviously it will not be working. If there is any auxiliary battery, the power will be supplied from the auxiliary battery or the supercapacitor.
Ma'am,
Is it
next
okay?
question is yes, ma'am. Next question is, what safety features are incorporated to prevent thermal runaway, short circuit, or over voltage conditions, ma'am.
So if you consider the over voltage condition of the charging station or the in this particular system, but well, like is this question related to this or any other the one which I have shown last? Is it
Ma'am,
related to
I
this
hope it is for the charging.
this one or the later one?
This one, ma'am. This one.
So first of all, you can see here. So like whenever there will be a system, so like if it is, if you are considering the system after the battery, again like battery is like already having voltage limit, right? So obviously these devices will be suitable to handle. So if you consider the device point of view, it is having the like very short time it will be able to handle high current or short circuit current, and after that obviously it will disconnect whenever there will be closed loop. Obviously it will detect that particular situation and it will disconnect the operation after the battery part, right? Before the battery part there will be isolation. So isolation will obviously that particular whenever it will see any situation of short circuit or any fault condition is there, so it will again disconnect the entire system where it is actually charging from. So it will be through the sensing the voltage or the current which is actually coming. So if you are considering the charging side, it will sense the charging side voltage and current, and after battery again like the converter whenever it is operating, it will sense the voltage and current, then only it will actually disconnect the operation of the system. So that kind of safety feature is incorporated in this system. Other than that, additional safety feature is required to look into. That particular part is not included yet.
Ma'am, one more question, ma'am. Can the heat mode be selectively controlled based on external input or battery management system feedbacks?
It is battery management system feedback. No
Okay.
external part is there.
Okay, ma'am. Okay. One more question, ma'am. How is vehicle to grid power transmission is done, ma'am?
So like vehicle to grid power, so like okay fine. So whenever we are considering all the vehicles, right? So if we consider okay this system, so basically what will happen like from grid, so obviously power will be transferred to the like some DC link or maybe it can go to the grid, right? Sorry, vehicle battery. So so depending upon that, so we have seen, so basically there is a big demand of the power for very like like limited time, means like during the morning office hour, so like 10 to 2 p.m. So in that time or the evening time 6 to 10 p.m. So in that time peak power demand is very high, and if we consider the EV integration in the existing power architecture, so then what will happen, this demand will actually go beyond the like given maximum limit. So then what will happen if this is going beyond the given maximum limit, so that will cause problem in the power system. So basically in the grid, so basically there will be power quality problem, so that will not only impact the other system connected to it, but also there will be harmonics generated due to that, because you know like if we have like overloaded kind of system, it will overload the transformer, it will generate, it will cause some harmonics to be generated, again like voltage drop will be there. So all these different problems will be there. In order to prevent that, what can be done, if it is possible to reduce the peak power demand during the this peak hours, means like let's say 6 to 10 p.m. or maybe 10 a.m. to 2 p.m. In that time what we can do, if the power demand is very high, again like that will be predicted in advance. So then like the batteries, so as I said, so this swappable station, so the batteries will be connected here or some fixed like vehicle will be connected here. So then what will happen, so those batteries if it can provide additional power which is beyond the maximum limit, you get the point. So that much power if we can provide from the vehicle, so it will go from the battery to the grid. So like generally we get power from grid to battery, so from grid it will go in the forward direction to the battery. So now we will provide it from battery to the grid. So during this peak demand hour, so then what will happen, the impact on the grid or the pressure on the grid can be reduced down. So that is the idea. So that is why it is like So like during this time period, it will be configured such a way that all the batteries will be connected, or the vehicle which will not be in use, it can provide power to the grid. For that, some incentive can be provided. So those things are still like people are working out how it can be done. Or maybe people, we can actually ask people to charge in different time rather than the peak hours. For that, like prices probably will be less. So that will help to shift this peak demand hour from a certain time to, like, it can be actually divided. So like due to the EV, whatever pressure, extra pressure will be there, it can be shifted from this peak demand hour to some other time. This is the main idea. So that is why vehicle to grid operation is also important. Does this
Ma'am,
answer
one
my
last
your
question, ma'am.
question? Yeah, yeah.
Yes, ma'am. Yes. One last question, ma'am. What safety mechanism are in place to prevent overheating or overcurrent conditions during battery heating and power transfer operations, ma'am?
Okay. Safety, battery heating, as you said. So in this particular case, as you have mentioned it rightly, so battery heating is actually one of the main problems in case of EVs. So at this moment we are using external heating. So we are not using internal heating, external heating we are using. So the different actually material, phase change material we are actually using to see how this external heating can take off the heat during the overheating period of the battery. So those kind of solutions we are looking forward. And another important method we are also exploring, actually liquid cooling kind of solution for this this particular time. So still we are exploring that particular thing. So these are the two things we are still kind of like yet to use it in actual system.
Ma'am, thank you very much, ma'am. Thank you very much for
Thank you,
accepting our
thank you.
invite, ma'am, and also explaining the traction method in EV wide band gap. It was really an eye-opening session, ma'am, and many things were new to us. I hope it will be useful for all the participants who are joined today. Ma'am, thank you very much for accepting our invite, ma'am.
Thank you for inviting me. Thank you. It was really nice talking to
Thank
you.
you, ma'am. Thank you,
Thank
ma'am.
you. Okay, okay. Bye bye.
Participants, the feedback link is posted in the chat box. Kindly fill the same. Uh, the meeting will be open for next 10 minutes, so you can fill the feedback and complete it. Thank you. The session is formally closed.